there's two jokes about this that circulate inside the company. You have a problem and you decide to use Java. Now you have a problem factoring. And the other one is you have a problem and you decide to use Python. Now you could have anything. It could be a list, it could be a string, it could be a problem. So don't get me wrong. I'm pretty fluent in both of these languages, and I like very many things about them. But Go is a deliberate attempt to try to do something different, and to some extent it's experimental, and we'll see how we get where we get. But some of these decisions are more well informed than you think if you just read the spec. So the syntax of Go is really clean. I don't know if you know from the introduction to the C programming language by Kernighan. It starts with C is a small language, so this is a small book. So Go is an even smaller language. By count of reserved words, it's smaller than C even, although it's an nonsensical measure of complexity of the language. But for example, there's only 4. There's not while, there's not do while, there's not, there's just 4. And 4 is generic enough to handle all the cases that you want. Also, semicolons, if you use languages with semicolons, you must have noticed that most of the time, these are the stupid places that the compiler should be able to figure out himself. So, the Go compiler figures out most of the time where the semicolons go, so you don't have to. And then the Go int will strip them for you. Of course, it's trivial. Then ideal constants. I should maybe talk about them after the types. To get rid of the type system tyranny, types are, Go is mandatorily strong types. So if you say it's an int, your function wants an int, you'll be sure to get an int, otherwise it will complain. But wherever possible, the types of things are inferred from. So you don't have to declare things in seven places and then make sure that these are consistent. The language is thought out in such a way that this is done by a compiler. One thing that helps there is that constants are ideal and will magically be converted to the right type. So numeric constants are infinite precision, infinite long things. And once you assign it to an int, the compiler can figure out you need an int. But other than that, casts are never implicit. So you always have to say, so there's no magic underground casting rules that turn floats into ints and vice versa, lead to subtle bugs. So it's very explicit, there's no magic rules going on. The package dependencies are solved in a very nice way. Namely, there's no such thing as a header and a body. But like in Java, the source is the source and that's all there is. It gets compiled to an object file. And if you have transitive dependencies of packages, then all the information, this is where I write. My God, it's full of, it's full of empty. Isn't it? Stop. So, if a package A depends on a package B, and this in its interface exposes concepts from C, then in the object file, so if 6G compiles it, if the compiler compiles it, then the public interface that's needed to understand B is in the object file. So when A is compiled, you don't have to go and read this. Now, this looks like a simple step, but if you think about the giant dependency graphs that you have in bigger systems, that's an exponential cost. So, and this is linear, so we have an exponential speed up. There, I proved it. I already mentioned it's mandatorily strong times. That is, if you have to say what it is, and it will check that it is without getting in the way. It's also memory safe. That is, there's no pointer arithmetic, and there's no casting from integers to pointers. Except if you really want to, then we have a package called foot. Shoot it yourself. So there's some low-level things where you can do system calls where you can disable this. But this also allows us to prove certain safety properties, which are essential if you run untrusted code in an environment like that. Because of this type safety, Go promises Go dangling pointers. If you make a pointer in Go, it will always be a valid pointer. That means it has to be garbage collected. And I mentioned this explicitly because I actually did the escape analysis part. Escape analysis is that if I try to ensure that the address of the variable does not leave a local scope, and then it can stay on the stack, doesn't have to be moved to heap. This means that it doesn't have to be garbage collected because it's automatic. And ironically, if I may tell an anecdote, I was most skeptical about this, about garbage collection in Go. And I told the team, and then Roos Cox told me, yeah, but for all these cases, the reason is that as a programmer that used to work mostly in C++, the lifetime of objects is my...
Okay, we do pizza sharing in a break and just concentrate on the talk.
Okay. I'll repeat this bit. Absolutely.
So I'll put a box here.
So this is anecdote time. I'll get to the interesting contact after the So I was skeptical about garbage collecting being necessary in language because as a C++ programmer, the first thing I think about is the lifetime of my objects and the ownership. First thing when I create something in the type hierarchy is worrying about who's going to create and destroy this.
Should we not distribute the pizzas first, then we can distribute them at the same time?
Okay, sure.
Can we reasonably efficient algorithm?
I'd say binary tree should work. So I'm going to give you this. I'm going to give you this. There, it works. Now, so and then Russ told me, yeah, but for all these cases where you can argue about the lifetime of an object, the compiler should be able to. And yeah, no. And then half a year later, it was my job to actually implement it. So, and he was right.
Yeah.
So, you have a t-shirt with a zombie gopher still, right? That's cool. Wow, it's really good.
No, that's from the Solar conference.
Oh. It looks like a zombie gopher. This is, did we over-order pizza? Where's Johan? Okay, so there's pizza for everyone.
I don't know. I have no clue. No, salami and... Everybody have pizza?
By the way, this is my colleague Marcel.
Hi there.
If you keep an eye on the changes that go in and out of the repository, you'll notice that Marcel is working on making Go the best internationalizable language ever, with native Unicode and the support.
In due time.
In due time. It's, well, it is already there.
Yeah, a lot of it.
Why then did you mix before English and German?
Did I make English and German?
The if.
Oh, that was because it was an example for my kids. So next
But
week,
shouldn't the if be in German?
that's because it's a keyword. There's only so much you do. Also, the compiler errors are in English. But if I have some time, I'm going to do Google Translate over the what's it called? Over there. Where you can type them in files. Playground. So I'm going to do Google Translate over it, so that at least the compiler errors will be encrypted German instead of this is for 8-year-olds. Besides, in Zurich, 8-year-olds get English in school. So if they should figure out that it's a related word. Where were we? But to your point, so the standard already says that source code is UTF-8 encoded Unicode, and so this is natively represented in Go, and it says something in the
Can you name method names?
Yes, yes.
So
And
you maintain if I get Chinese roll program?
you can. And
Problems with the capitalized later.
no, this is interesting. This is brought up by many non-Chinese speakers. There's okay, since we're all eating pizza, I'm going to digress a bit here. Identifiers and packages are exported if they start with a capital letter. And capital is defined by a standard Unicode attribute, what's it called? It's called capital letter. And immediately people said, this is a shame because this means that in Chinese you have no such concept as an export or not. And then Chinese people said, yeah, we don't want to name our variables Chinese names. Otherwise we'll just put a capital letter X before it to export it. And that works. So this objection was only raised by non-Chinese speakers, as far as we are aware. But yes, this is a. I will now demonstrate this. Ta-da!
So why did you choose to introduce this feature?
It's not, so we chose not to, or the design of the language chose not to restrict the character set to 7-bit clean ASCII. Because,
Why?
because we program for the world and not for US citizens. So actually, thinking too late about internationalization has been an evil that has taken years to root out inside our company. It's not just our servers, but per request, you can have people with different language settings hitting the same binary.
That's true, but this just creates more maintenance problems, it seems.
Why?
Because I cannot maintain this Chinese program with a funny letter.
Well, the fact that it supports doesn't mean you have to use it.
But it encourages that it's being used. So I'm trying to see if there's a good reason why you would want to say, "Keep this is okay, please name it in Danish and Chinese."
Fair point. I guess if somebody wants to write a program that's only maintainable by people that speak his or her language, they already had the means to do so in the UTF in 7-bit ASCII.
Yeah, that's a good point.
I've seen lots of Dutch code.
I can join you.
But there's also no need to restrict the character set of your I/O system different than the character set of your language. Interesting philosophical point. Let's get back to the main train of thought. So then there are two properties of the language that are actually my favorites, and I want to talk about some more. My favorite property when I just learned about the language were Go routines and channels, which are like Unix fork and pipes built into the language, which is no coincidence because Ken Constant wrote Unix and not I was born. But after having used the language for about a year, a bit more, my favorite property is the separation of interfaces and implementation, very fundamentally in the language. So Go has no inheritance. And the traditional way to think about program design over the past decade has grown into thinking first about your object hierarchy and then how these hierarchies interact, and then all sorts of sciences around reasoning about your object hierarchy have sprung up. And a problem with that, you might consider that often when you change something seemingly small in your object hierarchy, actually it invalidates your whole reasoning, your whole building. And so Go is none of that. In Go, you have classes, it's object oriented, and you have composition, you have very strong primitives for composing classes, but you don't have inheritance. And conversely, whether an object satisfies an interface, you don't have to declare, we'll see this in more detail the next few slides. You don't have to say, I will now make something that satisfies this interface. Here it comes, I derive from this interface, and here's the first method, and then the compiler says, yeah, you said that, you implemented that. So that's not how it works in Go. In Go, the interface is a set of methods, and then a type that implements methods with that name and signature satisfy the interface and can be passed to the user type. So let's look at that in a bit more detail. Here's a sample method program. All Go programs start with the name of the package. It's obligatory. If it's a program, there's a reserved name main. Then there has to be the import section, so that automatic, this is also done deliberately, so automatic parsing of your code and making tools for dependency management or something can do very simple parsing of the source. So the import is there, and here I make a type. In Go, type is declared by saying type name, and then define the type. A variable is declared by saying var name, and then specification var. A function is declared by saying func, and a constant is declared by saying constant. So after the package and import, we have only types, functions, and constant. Very simple. What we do here is we make the Go differs from C in describing types by doing it the Pascal way, or the more Pascal overall way. That is, if you just read what it says, it makes sense. Whereas in C, you have to sort of read the middle out to get the meaning of your type. So here we have a type, it's called vertex. It consists of a struct which has two members, x and y, which are of type float 64. You could say x float 64, y float 64, but if you write this, you figure that the compiler should be able to figure out what it means. So this is well defined. You can have more things of different types and list them together. Because they're capital letters, they are visible in other packages. That doesn't matter here. And now on this type, we can define a method. In fact, we define this method on pointer to the type. So func. The first thing between brackets here is this is called the receiver. So I think that this pointer is plus.
And that's all for today.
I'm going off time, aren't I? I should probably hurry up a bit. Because the receiver type is pointed to vertex, this counts as a method on this vertex thing. And now I can instantiate a vertex with, this is a composite literal. It's a way to make tables. It's very nice. And then I can call this and print this. So I can do this with any type. It doesn't have to be a struct. I can define an int. I can define something. I think I do that here. Yes. An example from the tour is, or from one of the talks, is that we define Fahrenheit as a float 64. and we define, but although then this example doesn't make sense, so let's stick to my float. So I have a float. There's no box around the float in the representation. This float is internally represented just like a float 64, meaning an 8-bit, what we call double in most C implementation. And now I have something with the same signature here. Namely something called ops returning a float. And now I have a separate category of types which are called interfaces, and an interface is a list of function signatures. The function is missing, but the ops, the argument list, which in this case is empty, and the return type are given. And now I can make a variable of this ops type, and I can assign it anything that satisfies this interface. And that turns out to be really nice in writing and composing programs. For example, there's a built-in type called error, which has a method that can turn it into a string. Now, anything that has this method can be used to throw around errors, and all code that expects to handle errors can deal with anything that does this. And after the fact, so the thing is, this does not pollute your dependencies. You don't have to say, you don't have to fit in that something inherits from some public interface. Another example from the package I/O is the reader and the writer. The I/O package defines some primitives that work with anything that can read from a slice like a dynamically sized array, a bunch of bytes, and write a bunch of bytes. And the consequence is that if you, for example, have a compression package that reads stuff and writes stuff, you can stuff anything in that implements this read interface or implements this write interface. And you can also wrap things. This is a very powerful method. Wrap readers in things that themselves re-export the read interface, and then put compression over, checksumming over, so it's, you can layer your data streams very nicely. Another example that's rampant in all the standard libraries is the stringer. Anything that implements string. You can use the food package, which does printf like formatting of strings, and it just says this is the thing that can format itself. And then whatever you pass in that satisfies its interface will be printed using its own method. Without that thing knowing about format, or without format knowing about that thing. So, to recap, a method can go on any type, or a pointer to a name type. The interface is a set of methods, they're orthogonal, and a value interface method, which could be a loose variable, but it could also be an argument. To a function, will be statically checked that it only gets things that could possibly satisfy this method set. So you have your static typing, but you still have dynamic typing. Yeah, you don't have to go around in several places to say that this implements that and I implement them, and I will now be cast to something that all works out of the box, which is very powerful. So the other thing that was my previous favorite thing about the language is built-in concurrency. A Go routine is a lightweight thread managed by the Go runtime. I can't stress this enough. If you're used to programming threads and you make your binaries with threads, you know the problem of having to guess a stack size that will do. And if you have 10,000 threads and you guess that 64K is a nice minimum stack size for your threads, then you have 10,000 times 64K allocated. And this can be a problem. A Go routine is a cheat thing. You can have 10,000 of them in your program, and it'll work fine. The reason it works is that before every function call, there are 3 instructions that check how big the stack is. And if it's too small for the next call, it will go allocate some more stack into the rest of the call. So this is a small price to pay for insane amounts of parallelism. For example, you can do very silly things computing parts of pi in parallel. There's an example somewhere on the program. There's an example of computing pi on tens of thousands of go-routines, which is a very inefficient way to do it, but it was just to illustrate the go-routines. There was a whole discussion on mayonnaise well, that's what we should do. No, it was just to illustrate. So anyway, the built-in primitive, Go, is a reserved word in the Go language. Not be confused with the Go tool. What Go is, it's like the background in Linux. It will run fx in a separate routine. The return value of f is lost. You can't get it back in any way. Instead, you have channels. Channels are a built-in communication mechanism. You can sample them. So if ch is of type channel and v is a value, then this is the way to send it, and this is the way to receive from the channel. And the channels are strongly typed, as is everything in Go. So if you have channel ints, you can only send ints, and if you file open language, you send anything else. So in that sense, they're not like Unix bytes. And you can do interesting things. So it's cheap to do things in parallel. Here's a little worker routine that takes a slice of ints. Remember, this very long length array thing. It sums them. The for loop has a special range variant of the for loop. This is how you sum up something in an int, in a slice. Here we create a slice, here we make a channel. We do the sums in parallel, and x and y wait to receive from the channel. So, we don't know which of these will finish first, but this statement will be done when both of these have passed. And this is an example from, I think, the tour. So to show that parallel, I say concurrency is a really cheap thing to build into your program. Concurrency is not the same as parallelism. Concurrency is a way to structure your program into chunks that you can reason about because their logic is confined to this little block that has things coming in and things coming out. It enables idioms that you might not have lying around in other languages easily. For example, here is a timer outer, which is go a func. This is the thing up here is a function literal. So we define a function on the spot, and it will be compiled to real code by the compiler at compile time. What this thing does is it sleeps for a billion nanoseconds, so that's a second, and then it will send a Boolean value true or timeout. And here's the built-in select, which is like our built-in primitive keyboard. It's like a switch, except it's a switch specially geared to receiving or sending from or to channels. This one will find one of the channels on which the operation will work, and then take that branch, and if multiple are ready, it will take a random. So it's like the select system call, except it's much cheaper. And it has, yeah. So, it's not parallelism, but parallelism is a consequence of having a concurrent program. If your program is structured in a concurrent way, then you can easily distribute it over multiple cores, and that will all be visible. One of the things Rob likes to repeat or iterate or say is instead of communicating by sharing memory, you should share memory by communicating. So the traditional way of having a block shared memory in mutex and having all your threads worry about the mutex and proving that your threads are doing the right thing with mutexes is way more complex than sharing state by sending it over a channel and being able to reason about the little box and the channel that go in and out. And so that's really nice. So I've now done twice as long as I intended about this talk. So I think it's time to take questions and pizza. And hand it over to, I hope it gives you a bit of a feel of how to try out Go if you haven't for it.
A simple question. What is included in the standard libraries right now, and what will be available in your future? What hasn't been included yet?
show you on the computer. These are currently the standard packages in the weekly release. There's compression, there's crypto, there's randomness, there's math stuff, there's working with binary formats.
This is a stable release.
Yeah, I'm gonna come to that. There's different ways to encode things. There's some experimental stuff that Marcel is working on. So this is recent